We're going to look at problems involving more than one object. So Newton's third law is going to be applicable, understanding how the objects interact with each other. So for example, let's say we're moving, so we're packing boxes. Being the lazy person that I am, I get my boxes sitting next to each other, and then I'm going to push from the side to get both boxes to move across the room to where I want them to be. Okay? So let's call this box 1, so it has mass m1. This is box 2, so it has mass m2. Oh, I don't know. 5 kilograms. 12 kilograms. Okay, let's say I push with a force of 120 newtons. There's going to be some friction between my boxes and the floor. How big it is depends upon what type of floor it's on, if it's on carpet or my vinyl or tile or whatever you might have. Let's say we're on something relatively smooth, so the coefficient of friction is not too big. So maybe 0.1 for our coefficient of friction. I want to know a couple of things. I want to know what the acceleration of our boxes will be. And I would like to know how hard box 1 pushes on box 2. Or vice versa, how hard box 2 pushes on box 1. Since they're touching, since they're moving together, there's an interaction between them. Box 1 pushes on box 2 pushes back with the same amount of force. Newton's third law. For every action, there's an equal and opposite reaction. So those are the two things I want to find. Now, it is, in terms of finding the acceleration, I'm assuming I'm maintaining this force, at least for the problem. So that 120 newtons is being maintained for as far as our problem is concerned. So, my boxes, what can you tell me about their respective accelerations? They're going to be the same, and they're going to be constant. So box 1 and box 2 will both have the same acceleration. They're moving together, side by side, and that acceleration will be constant as long as we continue applying this force. Exactly right. So to find the acceleration, it's perfectly valid to treat them as if they were 2 boxes with a total mass of 17 kilograms. And look at the net force as a whole. So the forces on our box, we have our 120 Newton force to the right. We have a normal force from the surface, the floor, pushing up on the box, or boxes. We have the force of gravity, and we have some friction. So there's 4 total forces acting on the box. Approaching this the same way we have other problems, looking at the net force in the x direction, so the horizontal direction, we have 120 newtons to the right, and we have friction to the left. Now I'm going to go ahead and substitute in. We know friction force is equal to the coefficient of friction times the normal force. Those are the only forces acting in the x direction. So by summing those up, we have to equal the mass of the object, which is the total sum of the 2 mass boxes, times the acceleration of the object. Okay with that? So very much like other problems we've been doing. We need to look at the y direction as well. In the y direction, we have the normal force upwards. and the force of gravity downwards. Now force of gravity, I'm going to go ahead and make the substitution, mg. But it's the total mass, m1 plus m2, g. Because we're treating it as one big old box. Total mass of 17 kilograms. That has to equal the total mass times the acceleration of our box in the y direction. But what do you expect the acceleration in the y direction to be? 0. So that tells me the normal force is equal to m1 plus m2 times g. I'm going to substitute that in over here, since the force of friction depends upon the magnitude of the normal force, just how big it is. I'm going to substitute that in. So the normal force is m1 plus m2 times g, in this case. We know the coefficient of friction is 0.1. We know the total mass is 17 kilograms. We know g is 9.8 meters per second squared. And again, the total mass is 17 kilograms. So solving for the acceleration, I get 6.08 meters per second squared. Anyone else agree?
Yep.
Now, with that sort of acceleration, we're not going to be able to keep up with the boxes for very long. So we're only answering the question during the period of time when we are applying the 120 newtons. An acceleration of 6.08 meters per second squared means the velocity is increasing by 6 meters per second every second. So after a second, you will be running at 6 meters per second. After 2 seconds, you would have to be running at 12 meters per second to keep up with the boxes. So we wouldn't be able to maintain that. But we'll still continue to answer the questions for the period of time when we are pushing with that force. So as long as we push with the 120 newtons, and as long as our boxes do not travel onto a new type of floor, this acceleration will be constant. Okay. So the acceleration now we know. Questions on getting the acceleration? Notice, in our picture here, there's no drawing of the force of box 1 pushing on box 2, or box 2 pushing on box 1. That's internal within the system. That force doesn't show up if we look at the system as a whole, if we look at both boxes as the one object. If we want to find the force of box 1 pushing on box 2, or box 2 pushing on box 1, we need to look at either box 1 or box 2. One or the other. It doesn't matter which one. Because the force will be the same. So for example, if we look at box 1, what forces do we have acting on box 1 just by itself? It has its own normal force, yes. It has the force of gravity, yes.
Drag
There's friction. There's the 120 newtons pushing on it.
Box 2 pushing on it.
Box 2 pushing on it. I'll just call it force of 2. okay with that? Let's go ahead and draw the picture for box 2. We'll only write the equations for one of them. It doesn't matter which one we do. But let's draw the picture so we know what the picture looks like for box 2. Box 2, of course, will have its own normal force and its own force of gravity as well. What else will be acting on it?
Friction,
There will be friction.
120.
It will not be 120.
Box 120 minus. Box 1.
Box 1. F1 and F2. They're the same magnitude. Box 1 pushes as hard on box 2 as box 2 pushes on box 1. They're just in opposite directions, that's it. Why is the 120 newtons not on here? Because we're not physically touching this box with our hands and pushing on this box with our hands. Okay? The 120 newtons will certainly help determine how hard box 1 is pushing on box 2. But if the 120 newtons isn't physically touching box 2, then it doesn't show up in the diagram. The 120 newtons was important in determining the acceleration. So the 120 newtons is, in a roundabout sort of way, taken into account. It's just not directly on there. Okay? Now we can go ahead and look at either box and look at the net forces on the boxes. Which one would you like to do? 1 or 2? One, 2. More opinions for box 1. It doesn't matter. Okay? It's going to work out either way. So if we look at box 1, net force in the x direction for box 1. Well, pushing to the right, we have 120 newtons. To the left, we have friction, mu times the normal force. We also have box 2 pushing to the left. So that's our net force in the x direction. So that has to equal the mass of this box times its acceleration. So the net force, adding up all the forces acting in the x direction, they have to equal the mass of our object times the acceleration of our object in the x direction, which we know. We know the acceleration. We already figured that out. In the y direction, we have the normal force upwards. We have the force of gravity downwards. The force of gravity is mg. The box we're looking at has mass of m1. So m1g is our force of gravity. That has to equal the mass of our object times the acceleration of our object in the y direction. But as we said before, the acceleration in the y direction is 0. So that makes our equation equal 0. So the normal force equals m1g. Plugging that back to the first equation we've drawn. 120 newtons minus our coefficient of friction, our normal force is m1g, minus force 2 equals m1a. Bringing force 2 to this side and m1a to the other side. I'm going to plug the numbers in while I'm at it too. Mu is 0.1, m1 is 5 kilograms, g is 9.8 meters per second squared. We're going to have minus m1a, so minus 5 kilograms. A we already found out to be 6.08 meters per second squared. That all has to equal force 2. So plugging and chugging at this point. get 84.7 newtons. Anyone else agree? You plugged it in? Thank you. I'm not very good at using these things. My calculator died, so. Now, why didn't we get a negative sign in our answer? Very easy answer to that.
Pushing in the same direction.
It's negative in my picture.
But it's, box one's pushing the same as box two.
It's just magnitude.
Just magnitude, because we already put the direction in there. We already put the negative sign on it. So whenever we put the negative sign in our equation, we're going to get the magnitude out. So this is the magnitude of F2. It is to the left, that's true. So box 2 pushes on box 1 with a force of 84.7 newtons. Box 1 pushes on box 2 with a force of 84.7 newtons. Just in the opposite direction. Okay. This is the contact force between the two boxes. If we had set up the equation for box 2, we would have had F1 minus force of friction equal M2A. Normal force would equal mg, but it would be m2g. So we could walk through and do the same setup. The difference is we only have 2 forces in the x direction on box 2 instead of 3 like we have on okay. Questions? So we're still applying what we've learned. We're still drawing our free body diagrams. We're still writing out the equations in the x and y direction, setting them equal to ma. Conveniently, a was 0 in the y direction. Making substitutions along the way until we get to what we're looking